Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to continue what we started last lesson. It's about the molecular orbitals. Today we're going to study the molecular orbital configurations. Our objectives for today are to define and calculate the bond order. We need to understand what is meant by the bond order and how we calculate it. Is to write also the molecular orbital configuration for some homoneuclear diatomic molecules. We need to determine if a molecule is diamagnetic or paramagnetic. Also, to explain if the molecule is a stable molecule or not stable according to the value of the bond order. So, I put, guys, this diagram in order to recall or to check our understanding from the first video. If you understand this diagram about the bonding and the anti-bonding and how they look like the bonding and anti-bonding molecular orbitals, then you are fine. If you have a problem recognizing this diagram, so I recommend you to go back and to watch the previous video. What is meant by the bond order? The bond order is the number of the bonding pairs of electrons between two atoms in one molecule. That means basically it's the number of the bonds between two atoms. And to calculate the bond order, we use this equation. It equals to half the number of electrons in the bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals. Let's check now those examples to understand better how we solve it or how we calculate the bond order. For example, if you're talking about the H2 positive, that means it consists of one atom of hydrogen and one ion of hydrogen. The atom of hydrogen, the electron configuration is 1s1 because the atomic number of hydrogen is only 1. That means the valence electron is only 1. And for the other species in H2 positive is going to be the hydrogen ion. And that means we don't have any electron in this H positive. Now we're going to use this diagram of the molecular orbitals. We're going to put for the first atom or the first species one electron in 1s, that is the atomic orbital, and this is the molecular orbital. And for the second species here is not an atom, it's an ion, which is H positive. So it has 0 electrons in 1s. We follow the off-power rule in order to distribute this electron. So it's going to be 1 electron in sigma 1s. The bonding or the bond order now, to calculate it, we need to use this equation, which is half multiplied by the number of electrons in the bonding molecular orbitals. We have only 1 electron, minus the number of electrons in the anti-bonding molecular orbital, which is 0, which equals to half. That means the bond order for H2 positive is half. What about if we want to do it for the H2 now? Also H, the first atom is 1s1, and the second atom also 1s1. So for the first atom we have 1 electron in 1s. For the second atom now we have 1 electron in 1s. And when we distribute it according to Hund's rule, we're going to put these 2 electrons in the sigma 1s orbital. So basically we have 2 electrons here. The bond order for H2 is going to be half multiplied by 2 electrons minus 0 electrons in the sigma star 1s, which equals to 1. So let's compare now between H2 positive and H2. As you can see, the bond order for H2 is greater than the bond order of H2 positive. That means H2 is more stable than H2 positive. Also, these numbers, the bond length and the bond energy, they also give us a hint about the stability of the molecule. As you can see in H2, we have a shorter bond than the H2 positive. And we have, for the H2, we have more energy for this bond to break down in H2 positive. That means in H2, to break this bond, we need more energy. We need 436 kilojoule for each mole of H2. And therefore, this is more stable because we need more energy to break this bond. These numbers, as I told you, they're not for memorizing. The number of bond or the value of the bond order, we need to know how to calculate it. So basically, it's going to be the number of electrons in the bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals multiplied by half. I want you guys to pause the video and try to compare between He2 positive and He2. All right. The second objective here is to understand what is meant by the diamagnetic molecule and the paramagnetic molecule. What is the difference between them? So let's check. Diamagnetic molecule is when we have paired electrons in the outer orbitals. That means, for example, in the molecular orbitals, px, py, and pz, as you can see here, we have double electrons, 2 electrons in each orbital, and we call it diamagnetic. Whereas when we have only unpaired electrons, as you can see, single electrons, even if we have 2 here, and only 1 here, that means it's going to be unpaired electrons, and we call it paramagnetic. It's a very important question in the exam. Let's check some examples to understand how the questions come in the exam. Properties of homoneuclear diatomic molecules of the second period elements in the periodic table. So we took these examples, Li2, B2, C2, N2, O2, and F2. I want you guys to pause this video and check the sequence of these molecular orbitals and what is the difference between this sequence and this sequence here. We have only one difference, and I want you to check what the difference between these two atoms and the other atoms, because these sequences, the two sequences, are separated by this line. So pause the video and check the difference in these two sequences. All right, now let's check, for example, for Li2. In Li, we have 3 electrons. That means we have 1s2 and 2s1. The valence electrons are 1 electrons in the outer shell. We have 2 atoms. So the first atom has 1 valence electron and the second atom has another valence electron. When we put them, we're going to put them in sigma 2s. Let's check the diagram. Lithium, it has here in this diagram, lithium, it has 1 electron in 2s, and the other lithium, it has 1 electron in 2s. So it's going to be sigma 2s, we have 2 electrons. The bond order should be, let's calculate it, 2 electrons in 2s in the bonding orbitals. So it's going to be half multiplied by 2 minus 0, which equals to 1. And what about this molecule? Is it paramagnetic or diamagnetic? As you can see in the outer shell molecular orbital, or the last molecular orbital, we have double electrons or paired electrons. That means it's going to be diamagnetic. Now let's have this example about the boron B2. So in the boron, we have 2 electrons, we have 5 electrons. So it's going to be 1s2, 2s2, and 2p1. So I'm going to use this diagram here. Look here, when we have p for the first atom and p for the second atom, as we know, each p we have px and py and pz. and we're going to write the molecular orbitals like this: pi 2py, pi 2pz, they have exactly the same energy. Then sigma 2px, then the pi star 2py, pi star 2pz, and then the sigma star 2px. In the boron, we have only one electron in p, so I'm going to write them. And according to Hund's rule, we need to do the single with the same spinning. So it's going to be one electron in pi 2 py and one electron in pi 2 pz. Now, how can we do the electron configuration? Always we start with sigma 1s, and we have 2 electrons. Then we have anti-sigma or sigma star for the 1s. Also, we have 2 electrons. Because here for B2, the total number of electrons are 10, because 5 each. So after sigma 1s, we have sigma 2s, and we have 2 electrons. After sigma 2s, we have sigma star 2s, and we have 2 electrons. Now we have 8 electrons. What is left is 2 electrons. We're going to put 1 in pi 2py, which equals to pi 2pz. Each one has 1 electron. And this molecule is going to be a paramagnetic molecule because it has single electrons or unpaired electrons in the outer molecular orbital. So let's check here. For the B2, we have in sigma 2s2, sigma 2s star 2, but this is for 2s. We ignore the 1s because it's the inner. And then we have the pi 2py, 1 electron, pi 2pz, 1 electron. All right. Let's check now another molecule, which is the N2. N2, for each nitrogen atom, we have 7 electrons. That means the electron configuration is 1s2, 2s2, 2p6, 2p5. So the valence electrons are 1s2, 2s2, and 2p3. The valence electrons are 5, and the outer most atomic orbital is in p. And we have 3 electrons. So I'm going to write for the first atom 3 electrons, all of them are single, the same spin. The second atom also single with the same spin. When we start to distribute, I'm going to put 1, 2, 3, 4. We still have 2, 5, and 6. The molecular orbital configuration for the N2 is going to be 1 sigma 1s 2, then anti-sigma or sigma star 1s 2, and then sigma 2s 2, and then sigma star for 2s. Also we have 2, and then after that we start with the pi, which is pi for 2p y, which equals to pi for 2p z. Here we have 2 electrons and 2 electrons, and the last one is going to be sigma 2px, and also we have 2 electrons. This is the electron configuration for the molecular orbital for N2. Now let's check. For this molecule, we have paired orbitals, paired electrons in sigma 2px molecular orbital. So it's going to be diamagnetic, as you can see for the nitrogen. All right. Now here, when we start for O2 and F2, the only difference between them is that we write sigma 2px before pi 2py and pi 2pz. Look at the difference, sigma 2px and then pi 2py, pi 2pz. Here we have pi 2py, pi 2pz, and then the sigma 2px. This is the only difference, and then we continue the same. And why are we doing this after the nitrogen? All right, we use this molecular orbital diagram when the atomic number of the atom is less than 8. So for the nitrogen, we have 7. For the carbon, we have 6. For the boron, we have 5. For the lithium, we have 3. So less than 8, we're going to write after sigma 2s, sigma star 2s, we're going to write pi 2px, pi 2py, and pi 2pz. But when the atomic number equals to 8 and greater, therefore, we're going to write after sigma star 2s, we're going to write sigma 2px right away. And after that, we're going to write, in terms of energy, the pi 2py and pi 2pz, as you can see here. So basically, this is for the oxygen, O2. For the oxygen, we have 8 electrons, so it's going to be 1s2, 2s2, and 2p4. Now in P, we have 4 electrons for each atom. This is atom 1 and this is atom 2. We're going to write 2, single, 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 and then we double one of them, 4 electrons and 4 electrons. Now we're going to start with sigma 2px, sigma 2px. Before we write the pi 2py and pi 2pz. When we distribute the electrons, we're going to put 2 and then single, single, double, double. That is 1, 2, 3, 4, 5, 6. And we have 8. We still have 2 electrons. So it's going to be single and single in pi 2py sigma, star, and another pi star 2py. 2py and 2pz, but the star. Now let's check the bond order here. The bond order equals to half multiplied by all the bonding orbitals. It's going to be 2, 3, 4, 5, 6 minus 1, 2 in the anti-bonding, so minus 2, which equals to 4 multiplied by half is going to be 2. And we know that the oxygen, because it has 6 valence electrons, is going to have double bond with the other oxygen atom. That's why the bond order equals to 2 here in this case. The bond order is 2. And of course, this molecule is going to be paramagnetic because we have single or unpaired electrons. Let's practice. Problem number 1. All right. Use a molecular orbital energy level diagram to predict the bond order in the F2 molecule or diatomic molecule. Is this stable species? All right, let's check. Now we have this bonding orbital, and F, it has 9 electrons. It's greater than 8, and the electron configuration should be 1s2, 2s2, and 2p5. That means in 2s we have 2 electrons, and in 2p we have 5 electrons. Let's start. We have 2 electrons in each atom. This is atom number 1, and this is atom number 2. All right. We start with the sigma 2s. We put 2 electrons. Sigma star 2s, also 2 electrons. Now in 2p, we have 5 electrons. 1, 2, 3, 4, double, double, and single. In 2p for the second atom, also we have 2, single, 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 and then we double them. Now let's distribute them. We always start because it's greater than 8, the atomic number. So it's going to be sigma 2p x is before pi 2py and pi 2pz. Let's distribute those electrons. We have 2 electrons up and down. That is 2. And then we have single, single, and double, opposite spin. That means now we put 1, 2, 3, 4, 5, 6 out of 10. We still have 4 more electrons. So I'm going to put 1, 2, and then 3 and 4 in the pi star 2p y and pi star 2p z. Let's check the bond order. It's going to be half multiplied by, in the bonding pairs, 1, 2, 3, 4, 5, 6. In the bonding orbitals, I mean, 1, 2, 3, 4, 5, 6. So it's going to be 6 minus 1, 2, 3, 4 minus 4, which equals to half multiplied by 2 equals to 1. And of course, because we know that the fluorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, and 7. And the second fluorine also we have 7 valence electrons. They are bonding together by a single bond. That's why the bond order is 1, because it's a single bond. All right. The second problem, use the molecular orbital diagram to predict the valence electron configuration, bond order, and likely existence of Na2 negative or Na2 negative ion. Now, for the Na, we have 11 electrons. The electron configuration is going to be 1s2, 2s2, 2p6, and 3s1. But for the other sodium, because it's positive, because it's negative, so it's going to have 1s2, 2s2, 2p6, and in 3s we have 2 electrons because we have a negative. So it's going to be Na2 negative. That means we have 1 more electron in 1 atom. So the first one in 3s, we have 1 electron, and the second ion, or the second species, which is an ion, a negative ion, we're going to have 2 electrons. Now, in sigma 3s, we're going to start distributing the electrons. We have 2 electrons, and in sigma star 3s, we have only 1 electron. So the bond order is going to be half multiplied by 2 minus 1, which equals to half. It has a little stability, but not too much stable, because this is the bond order, which is lower. It's greater than 0. That means it might exist, but because it has half, not 1 or 2 or greater, so this species or this ion Na2 negative, it's likely to exist, but not not very strong or not very stable species. It's very active, so it can react with anything to change its this species. All right, I hope you guys learned something new today. We're going to have one more video about all the problem solving for the molecular orbitals. I hope you guys learned something new. If you have any question, just write it in the comment and I will read all the comments and I will answer your questions. Have a nice day. Bye bye.